This lesson is the first lesson in our System of Equations unit. Our previous unit, we solved or graphed or wrote equations of singular linear equations. We just looked at them one at a time. A system takes actually multiple linear equations. Here's kind of an official definition. A system of equations is when you consider two equations simultaneously. And the word simultaneously means at the same time. So for example, here's a little system. Y equals 3x plus 1 and y equals 1/2 x minus 5. If I were to write a problem that would require graphing or examining both of these equations, this would be considered a system. Systems have solutions. When you have one linear equation, you actually have multiple solutions. Well, a system of equation is a little bit different. It's an ordered pair or ordered pairs that satisfy both equations. So let's look at that. Which ordered pair here is a solution to this system? Okay, so I have the system y equals 2x and 7x minus y equals 15. These are two completely different equations, and I want to find an ordered pair that is a solution to both of them. So all you have to do is just substitute. It's kind of like a guess and check thing. -2, 1. So I'll put in 1 and -2 into both of these equations. There's my first one. Does 1 equal 2 times -2? No. So it does not solve the first equation, so we can go ahead and knock it out of the running. All right, let's try the next one. 4, 5. Does 5 equal 2 times 4? Well, 5 does not equal 8, so no. 4, 5 is not a solution to this system. Okay, let's try 3, 6. I'll plug 3, 6 into the first equation. Does 6 equal 2 times 3? Okay, it does. It works for the first equation. You have to try it for the second equation in order for it to be a system or a solution to this system. So let's put it in the other one. That would be 7 times 3 minus 6, and you have to ask yourself, does it equal 15? Well, 7 times 3 is 21. 21 minus 6 is 15. So yes, 3, 6 is a solution to this system, because when I plug in the x value 3 and the y value 6 into both of these equations, it satisfies both equations. Try this one out on your own. Determine which ordered pair is a solution to this system. You can press pause and work all 3 points, and then press play when you're ready to find the answer. All right, hopefully you've discovered that B, the ordered pair 1, 5, is a solution to that system. When I plug in the x value 1 and the y value 5 into both of those equations, it satisfies them both. So one way to find a solution is to just try multiple pairs of x-y combinations, but let me tell you, it's going to take you a long time. There are actually some really efficient ways to solve systems or find those ordered pairs that are solutions to them. There's actually multiple ways. We're going to spend today focusing on just one way. It's called solving by graphing. In order to do this, you graph both equations. And then you look for their point of intersection. Intersection means where do they cross? Because that point of intersection represents having an x and a y value that is on both lines. Let's work an example. Find the solution to the system by graphing. Okay, my system is y equals negative x plus 5 and y equals x plus 1. So your first step, graph them both. Both of these equations are written in slope-intercept form, so I'm just going to choose to use their slope and y-intercept to graph. So if I start with the first one, y equals negative x plus 5. That one has a y-intercept of 5 and a slope of negative 1 over 1. So I'll go down 1 over 1. And then with a straight edge, preferably, you can graph that line. Okay, the second one, y equals x plus 1. That line has a y-intercept of positive 1 and a slope of positive 1. So I'll move up 1 over 1. And so now what you do is you look and see, can I tell where these two lines are crossing? And actually we can. I can see that these two lines are crossing at the point 2, 3. This would represent the solution to the system. You never want to trust your graphing. Always double check. So I'm going to plug in 2, 3 into both of these equations just to make sure that it is the solution. All right, so in the first system, the first equation, that would be 3 equals negative 2 plus 5. Well, negative 2 plus 5 does in fact equal 3, so it works. But you have to check it for the other one too. So does 3 equal 2 plus 1? 2 plus 1 is 3? Sure does. So they check. All right, next example. 2x minus y equals 2 and x equals 4. This is my system, and I want to find the point that they have in common. I'm going to start with the second one, x equals 4. Remember at the beginning of the linear equations unit, I told you that these equations, people tend to forget about them, even though they're really simple. This equation, x equals 4, is actually a vertical line that crosses the x-axis at 4. So it's pretty straightforward to graph. The second equation, 2x minus y equals 2, it's written in standard form, and I'm going to try and graph this with the x and y intercept method. I'll kind of put my work over here. All right, the x-intercept. To find the x-intercept, I'm going to put in 0 for y and solve. So that would be 2x equals 2 and x is 1. And I'll put a point at 1. Then I'll find the y-intercept. So that means I'll put in 0 for x and solve for y. So that would mean negative y is 2. Therefore, the y-intercept is negative 2. Okay, so here's my line. Oh, and actually my grid isn't quite big enough. Extend it out a little bit. There we go. It looks like these two lines are intersecting at the point 4, 6. Okay, so to check the equation, 2 times 4 is 8. 8 minus 6 is in fact 2. Okay, so it works in the first equation, and then on the second equation, it's kind of hard to put in an x and a y when it's just x equals 4. But since the x value is 4, then it's obviously on that line. So here's your solution. Okay, try this next one. Pause it, work it on your own, and then when you're ready, press play. Okay, I'm going to choose to graph these two equations by putting them into slope-intercept form. Remember, we learned 3 different ways to graph linear equations. We learned how to make a table, how to use slope-intercept, and how to use the x and y intercepts. You pick the way you want to graph it. It doesn't really matter to me. I just want you to be able to graph it. So this first equation in slope-intercept form, I'm going to start by subtracting 2x from both sides. So that would mean that y equals negative 2x plus 2. So now that it's in slope-intercept form, I can very easily see that my y-intercept is 2 and my slope is negative 2 over 2. So I'm going to go down 2 over 1. And remember to use a straight edge. It's not so easy when you're doing it on a tablet. Okay, the other one, I'm going to put it into slope-intercept form also. So I'll start by subtracting x from both sides, which would mean that negative y equals negative x plus 4. And then I'm going to multiply both sides by negative 1. So positive y equals positive x minus 4. Okay, my y-intercept is negative 4. My slope is 1 over 1, so I'll move up 1 over 1. There you go. Can you see the intersection? Absolutely. My solution to this system is positive 2 for x, negative 2 for y. Great. Okay, let's try another one. Pause it, see if you can graph it, and then ask yourself, do you see the solution or not? These 2 lines, okay, the first one has a y-intercept of positive 1 and then a slope of negative 2 over 1. So it looks like this. The second one has a y-intercept of negative 3 and then a slope of negative 2 over 1. What do you notice about these 2 lines? Well, you should notice that they're parallel. And by definition of parallel, these 2 lines are never going to intersect. So when you have 2 lines in a system that are parallel, there is no solution. One way you can determine if they have no solution is just by looking at the slopes. When I saw these 2 lines in slope-intercept form, and I saw that this slope was negative 2, and this slope was also negative 2, and then they had 2 different y-intercepts, I automatically knew that they were going to be parallel. You can go ahead and jump to that conclusion that there's no solution, or you can graph it just to be sure. But no matter what, make sure that you tell me that there is no solution to this system. This next system is kind of similar. Try graphing them. I'm going to try graphing them using the x and y intercept method. So for the first one, the x-intercept means that I'm going to put in 0 for y and solve for x, which would give me that x is 4. For the y-intercept, that would mean I would put in 0 for x and solve for y. So in this case, the y-intercept is 2. So there's that line. Okay, the other equation, 2x plus 4y equals 8. X-intercept. I'm going to put in 0 for y and solve for x. 2x equals 8. Therefore, x will be 4. Isn't that interesting? I'll use a different color. Already I see that they share the point 4, 0. So that could possibly be a solution. Let's finish graphing though. If I want to find the y-intercept, I'll put in 0 for x and solve for y. So divide both sides by 4. That will give me that y is 2. Look at that. The y-intercepts are the same. So when you do this, you kind of have to ask yourself, at what points are these two lines intersecting? Well, they're intersecting at their intercepts, but they're also intersecting at all of these points. This would be a case where we would say that there are infinite solutions. Whenever you have two equations in a system whose graphs end up being identical, it means that they intersect infinitely times, so you can tell me that there are infinite solutions. So that previous one, the parallel lines with no solution, and this one where we have infinite solutions, those are two really important cases to remember. All right, we're going to do one last example. It's a word problem, and then we can call it a day. Tickets for the theater are $5 for the balcony and $10 for orchestra. If 600 tickets were sold and total receipts were $4,750, how many tickets were sold for the orchestra? So let's practice writing equation to model. How about we start with defining our variables? We have two types of tickets. We have balcony tickets, which maybe I'll use a B. And then we have orchestra tickets. And I'll say number of balcony, number of orchestra tickets. One equation I could write here. Well, let me just preface by saying, whenever you have two unknown variables or two unknown values, chances are you're going to have to write two equations or write a system. So if I have two unknown values here, number of balcony tickets and number of orchestra tickets, I need to try and write two equations to represent the situation. So how about I start with total tickets sold? The 600 tickets, that is comprised of both balcony tickets and orchestra tickets. So I could say B plus O equals 600. Okay, another thing we know is that total spent or total revenue here was $4,750. And then that balcony tickets were $5 each, orchestra tickets were $10 each. So I'm going to write a second equation. I'm going to say $5 per balcony ticket plus $10 per orchestra ticket equals a grand total of $4,750. Here's my system, and I'm going to cut you a little break and I'm going to show you immediately what the graph looks like. Here's a graph for tickets sold. Here's a graph for money. And then we can see here that if they sell 250 tickets, that's where that would give you the amount for each. We'll do some other examples of these. It's actually easier to solve these algebraically, but I'd like for you to see a graph. All right, so that's going to be it for today. Be ready to come to class next time with a straight edge and maybe some graph paper to graph on, and we'll do lots of practice solving systems by graphing.